things on the lab. And yes, welcome to electrostatics and the frustration associated with that, okay? Because that's the problem, is that it's so easy for your observations to become a part of that. So, some of you handled that very cleverly. You took a picture of the needle stick back behind, and then you made, little marks. Yay for technology. That was pretty cool. So, which oddly enough, that works off of the electric field, so that was kind of cool. So, the struggle was, and this is what this is always. There's two struggles with this lab. One is how you physically make the measurements, and the second one is how do you work the buoyant force into the problem? Okay, when do you use it and when do you not? So, when you put that balloon on the scale, right? Yeah. And let's say that you got, I don't know, 0.036 grams, whatever that was. Okay? All right? Or kilograms. Okay? So this is a pretty small number. So here's my question. Was there a buoyant force acting on that balloon when you put it on the scale? Well, there was, right? And that buoyant force was acting up, right? Just like if you try and push something like a ball underneath the water. Louise? Sorry. Oh boy. Step away from that balloon. Get away! This is for my sister. So, visualize this, and this is the analogy that I gave to some of you. Imagine that you're in a swimming pool, and you have your bathroom scale, and you stand in the bathroom scale like submerged up to like the rib cage, okay? So you look down, and it's reading 80 pounds, okay? Whatever that is, okay? You're standing in the swimming pool, and it's reading like 80 pounds. So you take that same scale, and you walk out of the water, and now you stand on that scale. What's the scale going to read? More than 80 or less than 80?
I guess less.
More, it's going to read more than 80. Why?
Because there's no
Yeah, you've lost the buoyant force that was helping support you. Okay? So on dry land, that without that buoyant force is going to be more. So when you have that balloon and you're getting a certain value, okay, whatever that number is, that's analogous to you being underwater and only getting a reading on the scale. Okay? So what you need is, hey, going, what would be the scale out, what would be the reading outside the water? Now here's the reason why. When you look at when you had those balloons suspended, those balloons had a certain amount of buoyant force on them, okay, because they were still in the air. You don't need to worry about it, and here's the reason why you don't need to worry about it. Because that was in effect taken into account when you weighed the balloons in air, okay? So when you weighed the balloons in air and you got a number, and you could say, okay, well, this is the gravitational field. This is the true value of it in the air, okay? So that's why when you're doing these calculations in air, you don't need to worry about the buoyant force, because that buoyant force is there. Then you can take that mass, multiply it by g, boom, that becomes the anchor of how you do everything else, okay? In terms of how you find the tension, how you find the electrical field. You didn't have to find the tension, but you could have, because the tension just would have been the hypotenuse of that triangle. So what the main thing you were after, and this is one of the most critical things I'm going to look for, how did you calculate that horizontal force, which was the electrical field force? So here's the whole assumption of this problem, is that the electrical force separating those two is going to be K, Q1, Q2 over distance squared, okay? So here's the tricky part. you've got to have that force. That was the horizontal component of that value. But when you do the distance, did you just use the distance from the center line out, or did you use the entire distance on centers between the two balloons? That's one of the things I'm going to look for in those calculations. So the beauty of this is that we just assumed that the two charges were equally the same. If they weren't, you couldn't find the solution. Okay, you just have to assume that the two values are the same. So that allows you to find the charge. You assumed they were negatively charged. Put away that red balloon. You step away from that meter stick. Thank you. So you're going to find those charges. That then is going to form the basis of everything else. So when you need the actual mass is when you're trying to find the gravitational force between them using big G M1 M2 over E squared. Now, was it much of a difference? Somewhat. Okay. But here's the point. The actual masses of the balloons, were those bigger or smaller than what you measured on the scale?
Smaller.
Bigger.
It should be bigger.
I remember doing this one. So.
Okay? And here's the reason why they're bigger. It's the same idea of the swimming pool. If you find your weight standing in the water and then go out of the water, your apparent weight is going to increase.
Yeah.
The same thing is true of the balloons. The actual mass of the balloons is bigger than what was on that scale because it had that buoyant force acting on it. So the actual masses that you use in this calculation here should be bigger than what they weighed in when you put them on the scale. Okay? That's where that buoyant force comes into effect. And remember that buoyant force is rho v g. Notice that that has a g in it, and your gravitational force also has a g in it. Okay? So that's the common theme. And if you look at this even in terms of rho v, that's density, which is kilograms per cubic meter. And then you have a volume, which is in cubic meters. The cubic meters cancel out. This is basically mg, which is the exact same thing. Okay? So rho vg is nothing more than mass times your gravitational acceleration. Okay? All right? Cool with the Latin. Ramesh, you have to understand that concept of what's going to happen on the test, which is on
Thursday.
Thursday. Thank you very much.
Thursday?
Okay.
I hate Thursday.
So, old school meets new school.
New school.
Today's the 3rd. It's on the 5th. Yeah.
What?
It's like,
Yo, it is this Thursday.
Wyatt, you're really smart.
He asked.
Who
No,
did?
you know what you're doing, buddy. It's okay.
What is that?
Who are you pointing to?
How many days of
9 weeks
Very
ago.
smart.
notes did you have from Thursday?
I'm proud of you.
Friday? 2 lines on
Why are you not taking my compliment? Why are you not taking my
Friday,
compliment?
Thursday and then Friday?
Hey, look, the balloon.
This might be really close.
No, my.
All of this? Yeah.
Put the meter stick
Because I put a new page
I'm gonna go
per.
take a nap.
If I
So,
left
I'm gonna sleep from like 3
one
to
page
like
in between
whatever I have to eat.
these notes.
You know, with, uh,
I think so, yeah. Because
you're kind of like the ball guy.
this is like some of the assignments.
I've never seen this
I
way.
don't think you need it.
I'm kind of like a mind.
Because sometimes you take more notes than I do, and sometimes I take more notes. Yeah, it goes both ways. Yeah. Okay, I'm using stuff right now. He hasn't changed much since I last looked, I'm not gonna lie.
Oh, yeah.
Wait, is pine green?
I still know I
No.
have to.
It
How
is.
do I draw that? I can't draw, bro. Stop drawing. This is not art class.
Like, we're just a, this is smart.
Wait.
This is a calculator. Wait.
Okay, so let's start with this.
What? I have no clue what you even said.
I don't know if that's good or not, but I'm good.
You are now.
We're talking about all this response.
You have a parallel plate capacitor. Each plate is 2 centimeters on a side, about like A, not very big. And it's charged to 20 nanocoulombs.
That's scary.
Find the strength of the electric field in between the two plates. So parallel plate capacitors, remember this is what makes your life livable in terms of cell phones. Parallel plate capacitors store charge. Okay? So only way this works is if one plate is positively charged and one plate is negatively charged. And you have to do work to do that. You hook it up to a battery, you plug it into a wall, you crank something, okay, do some mechanical work. Something has to separate these charges to build this up. So you've got dimensions, and you know that it's separated by 2 millimeters, which is remember millimeters about the thickness of your fingernail. So these are not separated by very far. So remember, what's on your equation sheet is a jacked up version of this. It has that Greek letter cow. Don't worry about it. Cow is 1. Okay, I will never let cow be anything different. So don't even worry about it. It's there. So, what's the epsilon naught?
Some number.
So you got 8.85 times 10 to the negative 12, right? And then, now, that area has to be in what?
I think that's what it's. I think
Meters
it's
squared.
what it's get to.
But you got 2 centimeters by 2 centimeters, about the size of a postage stamp. So, you got the 2 centimeters. 2 centimeters is 0.02 meters. And then we'll make it easy and make that a square. So somebody square that, and then boom, there's going to be your area. And it's charged to 20 nanocoulombs. Can you leave that in nanocoulombs?
No.
No, that has to be in coulombs. So, somebody take 20 times 10 to the negative 9 coulombs. You have epsilon naught, and then you have 0.02 meters squared. So, what do you get for the value of the electric field in between?
5.65.
5.65 times what? Times 10 to the 6. What are the units for electric field?
Newton over Coulomb.
News over coulombs.
Newtons over Coulomb. Okay? Cool. Now, here's the deal. Let's say that I want to take an electron and I want to shoot it across this gap, which is 2 millimeters wide, and I want to know how fast it has to be going to just make it to the other side and stop. Somewhat analogous to how fast would I have to throw the squirrel so that it reaches a specific height.
But it's not constant velocity.
Okay, if it was constant velocity,
Then it would not
how
stop.
could it stop?
You know what? I like that thought process. Yeah.
Okay, now, you have an electron. You have the strength of an electric field. What can you find knowing an electric field and that it's an electron? Force. You can find force. That force is going to equal what? Right? Okay? So, you know your electric field is 5.65 times 10 to the 6 newtons per coulomb. What's the charge on an electron?
1/6 of 1919.
1.6 times 10 to the negative 19 coulombs. If it was a proton, would it be the exact same answer?
Yes.
Yes, as protons and electrons have the exact same charge.
Right.
Right? So, Elliot, take that answer that you just found, multiply that by 1.6 times 10 to the negative 19.
9.04 times 10 to the negative 13.
9.04
4 times 10 to the negative 13.
newtons. Okay? Got that?
Yeah.
And you know the mass.
Where do you find the acceleration?
Yeah, I like it. I like our head on.
Okay, now that we know the force,
What's that?
so what were you pointing? Oh yeah.
Alyssa, focus.
Wow.
So here's the story. At the end of the game, or at the end of the day, is this thing going to, if you shoot an electron and you want to make it stop, and this is going to be important later on in the next unit when we get into electrical potential energy. If we want to make the electron stop, do we shoot it from the positive towards the negative, or from the negative towards the positive?
Positive to the negative.
Oh, I wasn't gonna answer that. What's the force that you just calculated?
I'll answer.
Okay?
Hey, I'll answer.
So the force that
Slowing down.
we just found is the force created by an electron with this charge existing within that electric field. So this is the force that's acting on the electron.
Okay.
Okay? We couldn't do it with the neutron because the neutron doesn't have any charge.
Yeah.
Okay?
Okay.
And that's just the charge on a single electron. Okay? Okay, now, what's your answer?
We're gonna. The positive is gonna push, right? We put it on the positive. The positive side's gonna push. The negative side's gonna pull.
This is like a 3-way.
I thought we were shooting an electron.
Shooting an
Yeah, we're
electron.
gonna shoot it positive to negative.
Electron.
It's gonna get
Oh, yeah,
pulled by the
electron,
positive.
negative to positive. Negative to positive.
No.
Negative to positive.
Negative to positive.
Yeah, I was thinking it
Final
was like
answer.
an electric field, like a pro.
Okay. So, we've got positive charges on this side, and we have negative charges on this side. So let's just back up for a second. What's the direction of the, leave the electron out of this for now. Okay, leave the electron out, step away from the electron. What's the direction of the field in that parallel plate capacitor?
Towards
To
the
the right
negative.
or to the left?
To the right.
Why to the right?
Plus pushes.
Positive test charge.
Right.
Positive test charge.
Positive
Right.
test charge in here, it would feel
Repulsion from the positive.
so. If this is how this is existing, the electric field is going to push
Please stop. I would greatly appreciate it.
this way. Okay? Got it. So, if I want to make an electron stop, do I eject it from the negative side or to the positive side?
Negative.
To the negative.
So I got an electron, which has a negative charge.
You want to send it towards the negative.
I want to send it towards the negative.
Yeah.
Why?
Because it's going to be pushed away and pulled by the positive. So it's
You
gonna
have
slow
two
it down.
things going in that consideration,
Drop
right?
it.
So you've got it. If you shoot negative charge here, it's going to be pulled back towards.
Oh.
No.
PC.
Go with dying.
Bring your
Plug it in.
So, if I push the negatively charged electron, it's going to be repelled by the negative and pulled back towards the positive. So this is like a two-dimensional gravitational field. So if I just take this baseball and throw it up in the air, it only feels an attractive. So imagine that you have like an anti-gravity field that not only slows it down, but pushes it down at the same time. Okay? All right. So here's what we've got. Now that we know the force, according to Sidney Woodard, what else can we do? We can do F equals MA.
No way.
I
didn't.
So
Greg, does that really work?
we've got
Okay, I'm sorry, Greg.
so somebody take that force and divide it by the mass of a single electron. And the electron's mass is
9/11 to the negative.
9.11 times 10 to the negative 31st.
31.
So, what do you get as the acceleration?
9.92 times 10 to the 17.
That's pretty fast.
Okay?
You know,
Meters per second
yeah, I put it
squared.
in my calculator.
Okay? That was my acceleration.
That was exactly.
Would the acceleration of a proton be the exact same?
No, mass is different. Finally.
It's just
The
got
mass is greater.
I said, what did I say?
You said different, you
different.
goose.
Yo, it's different. Oh my god, I didn't even catch myself. But hey, at least
Mass
it's
is greater.
basically.
So
I don't even disagree with that.
Put 'em on the
Because
nail
if-
then.
If you say same, the antonym of that is different. Yeah, same. No, it's different.
Yeah, I think that's a.
You could say unalike.
Put them on the nail then.
Dissimilar.
We need to
Okay.
actually.
Okay, first, mass increase, acceleration goes down finally.
So, what do you know about the mass of a proton compared to the mass of an electron?
So electron.
Mass of a proton
Bigger.
compared to an electron.
More massive.
So, here's the question. Would a proton feel the exact same force?
Yeah.
Because it has the exact same charge.
See.
But it's not going to have the same acceleration
Not the same mass.
because it has a lot more mass compared to an electron. Okay. So here's what I want to know. I've got, in this situation, a 2 millimeter gap. Okay? I have a 2 millimeter gap. I want to imagine this is the electron. I want to know how fast I have to launch that thing. So it basically, on this analogy, goes to a height of 2 millimeters.
That equation.
That equation.
Come on! What a pull. Oh my.
So if you look at v squared equals v naught squared plus 2ax.
No way.
What's the only thing you don't know?
V naught squared.
No B.
Because what's your final velocity going to be?
You
don't know
B naught.
Because it's going to stop just as it gets to the other side. So if I go v squared minus 2ax, square root of that, I get v naught. So I've got 0 squared minus 2. I've got an acceleration of 9.92 times 10 to the 17 meters per second squared. And my distance is 2 millimeters, which would be how many meters?
Berg, there's an issue.
A really small amount.
What's the
An
issue?
imaginary
Negative
number.
imaginary.
So here's the deal. So
Get rid of the
technically,
negative.
because of the fact that this is an electron,
Down.
It's
Wait, how many millimeters?
Oh my gosh.
that should be a negative value.
I like it.
I totally
Okay?
Brig, how many millimeters?
Anybody ever told you
2.
not to go?
Two.
What?
Wait, do we put it as like a negative in other equations, or is it just in this case just so it ends up being?
I just don't get it ends up. Okay? And basically, it's an absolute value kind of thing anyway.
I thought it was negative because it was slowing down.
You could, if you wanted to find that direction to be
It's
positive.
happening.
Oh, okay.
Okay, so what'd you get? Uh,
6.3 to the 8.
what'd you get?
I think 6.3 e to the 8.
What?
7.
I know.
No.
Wait, is it?
Wait, no.
You know what? Oh, someone else in there.
Oh my god, I have to work on that.
Really?
It should be the 7th, 8th, something like that.
Yeah. Yeah, that's 7.
What'd you get?
6.37.
That's literally what I got.
Yeah, I'm sorry. We
Okay?
had forgive me.
Not quite the speed of light, but pretty close.
Yeah, that's pretty fast.
Okay? You're not going to launch a squirrel this fast. Okay?
Really?
So, here's the next question. If that had been a proton,
That's like 21%.
You understand.
but if it had been a proton, your acceleration would have been smaller. So what would have happened to the velocity of the proton then? It would have been smaller because your acceleration would have been bigger. Okay. Also, would have the proton been shot in the same direction?
No.
Proton would have been shot in the opposite direction because it's going to be attracted
Why
to
is this one
the
negative?
negative and
So
repulsed
then
by the
it doesn't
positive.
make it
Remember,
imaginary
so-
number. Basically what he said.
So, which, is it the place? No, which direction did we say we were gonna go from?
Okay. So if this side over there is positive,
Yeah.
right? That side over there is negative. Okay. So we want that electron to just stop on the other side.
Yeah.
So I'm going to shoot it from the positive side because it's going to get pulled back towards the positive plate and it's going to get repelled by the negative.
Why would you shoot from the other side? So you just stop going one way.
No, because if you shot it on the other side, it would be speeding up as it goes across. You want it to stop.
Oh, okay.
Mara.
How's that 9.92 negative? Whatever number that was.
Acceleration.
Go down.
Because it's slowing down.
So it just depends on how you find it. There's one way you could do it.
No.
It's hibernating?
I can hibernate.
Why is it
I think
hibernating?
it's not plugged in.
Serious?
Are we all trying to compete for
It's unplugged in.
club, bro?
Dude, I think it died.
Looks plugged to me.
All three of you have to share because
Oh,
the more
yeah.
we do that.
Should I stop the video?
You all just counted. I didn't say that.
Ban